So let us see about transport phenomena. So in the transport phenomena, we see about heat transfer. So modes of heat transfer is generally conduction, convection, and radiation. So in conduction, temperature gradient exists through the solid or stationary fluids. So convection is which is occurring within a moving fluid or between a solid surface and a moving fluid when they are at different temperatures. Thermal heat transfer between two surfaces, often in absence of air, often intervening medium. So conduction. Fourier law of conduction. Q is proportional to minus A into dt by dx. Q is equal to minus Ka dt by dx. The thermal conductivity is the ability of the substance to conduct by varying in temperature. So K solid, K liquid, K gas, the relationship between them is K solid is greater than K liquid is greater than K gas. So your thermal conductivity is the ability of a substance to conduct heat and it varies with temperature. Now what else is there? So K solid is greater than K liquid is greater than K gas. If you see for 3D conduction, your Qm with respect to K is nothing but minus dou square T by dou x square plus dou square T by dou y square plus dou square T by dou z square plus 1 by alpha dou T by dou y. Now your alpha is nothing but K by rho Cp. If your alpha is increasing, it means the speed of propagation of heat into the material will increase if alpha is decreasing, which is nothing but coefficient of thermal diffusivity. So this is thermal diffusivity. If alpha thermal diffusivity decreases, heat absorbed by the material increases. Okay. Next. So case number one, if there is no heat generation, it means your Q by K is 0. So overall, you can write as dou square T by dou x square plus dou square T by dou y square plus 1 by alpha is 0. Steady state condition, dou square T by dou x square plus dou square T by dou y square plus dou square T by dou square equal to Q plus Q by K is equal to 0. For a 1D steady state, dou square T by dou x square plus Q by K is 0. So how to identify this? So heat transfer through a wall is dou square T by dou x square. So you don't have this, you have T is equal to C1x plus C2x, C2. So at what are your boundary conditions? X equal to 0, T is equal to T1, X equal to L, T is equal to T2. You put these values here, you'll get Tx equal to T2 minus T1 by L into X plus T1. So conductive thermal resistance is nothing but you'll write it as L by Ka. Conduction through a composite wall. So you have a composite wall which is made up of three different thermal conductivities, but temperatures are T1, T2, T3, T4. So now your this temperature is nothing but overall T1 minus T4 by overall these resistances are T1 minus T2 by this resistance, T2 minus T3 by this resistance, T3 minus T4 by this resistance. So parallel R1 is equal to L by K1 A1. R2 is equal to L by K2 A2. R total is 1 by R1 plus 1 by R2. So resistance for conduction, resistance for convection. You can write conductive resistance as L by Ka. You can write convection resistance as 1 by Ha. Heat transfer coefficients. So plain wall with internal heat generation. So you have a plain wall, maximum heat will be there at the center. You understand whenever you see a strong, very hot billet, every time the temperature will be maximum because from here to here dissipation is very difficult, but from here to here dissipation is very easy. So surface temperature will cool down slowly, partially than your temperature at the midpoint. So Tx equal to Tw plus Qm by L square by 2k into 1 minus x square by L square. You just put these values inside with boundary conditions, you'll get this. Conduction in a composite cylinder. So in a composite cylinder with radiuses R1, R2 and R3, your overall convector resistance is 1 by R is equal to 1 by HA R1 plus K 1 by K1 ln R2 by R1 plus 1 by K2 ln R3 by R2 plus 1 by H by R3. So Q is equal to delta T by R. So for a sphere, your R is nothing but 1 by 4 pi, 1 by HA R1 square plus 1 by K1, 1 by R1 minus 1 by R2 plus 1 by K2, 1 by R2 minus 1 by R3 plus 1 by HB R3 square. Biot number, internal conduction resistance by surface convection resistance. So this is nothing but conductive resistance to convection resistance, HLC by K. So what is convection? Convection can be of two types, natural convection, forced convection. Induced by density differences due to variation of temperature is normal convection. Fluid is forced to flow over a surface through external means such as fan or pump. This is called as forced convection. So Q is equal to HA delta T. Forced convection, convective constant will be convector constant will be greater than the natural convection coefficient. So velocity boundary layer, what do you call as boundary layer? Boundary layer is nothing but friction effects are mostly negligible here. The viscid region, friction effects are negligible. Frictional effects are significant. So in a boundary layer, frictional effects you will be seeing it. For example, see here at the surface, suppose a fluid is flowing like this. At this point, this is called as no slip condition where V is equal to 0. But away as you move, your velocity increases slowly. The same way thermal resistance. So tau is equal to mu into dou v by dou y. So mu is dynamic viscosity, kg meter per second, kg per meter second. Tau is equal to Cf rho V naught V infinite square by 2. Ft is equal to Cf A rho V infinite square by 2. Where Cf is drag or friction coefficient. So laminar region, slowly your laminar region is this. This is transition region where your velocity is changing slowly. So you are moving from laminar region to turbulent region. Turbulent region is where your subviscous layer will be formed. Till here there is no subviscous layer. Everywhere at the terminal velocity is zero, but here it is not. So Reynolds number, it tells you different, it tells you the relation between frictional and viscous force, inertial force and viscous force. So it is nothing but rho v L by mu. Nusselt's number is nothing but HL by K. Prandtl number is nothing but mu C by K. Schmidt number mu by rho DAB. Lewis number L is equal to K by rho Cp DAB. Grashof number, it tells you the relation between buoyancy forces and viscous forces. So it is d delta rho by v by rho v square. You get g beta delta t v by v square. Delta p is nothing but minus p beta delta t. This is nothing but volume expansion coefficient. So radiation, you can write it as E is equal to h nu h c by lambda. Black body is something which is perfect emitter or absorption of radiation. At a specified temperature, the highest energy is emitted by a black body. They emits radiation uniformly in all the directions. Loss of radiation, E lambda star is equal to C1 by lambda power 5 E power C2 by lambda t minus 1. Star represents black body radiation. C1 is equal to 3.74 into 10 power minus 16. C2 is equal to 1.44 into 10 power minus 2. Stephen Boltzmann constant. E star is equal to sigma t power 4. E star is equal to 0 to infinite E lambda star t lambda. So sigma is equal to 5.6 into 10 power minus 8. Wien's displacement law, lambda max is equal to some constant by T. Emissivity is nothing but ratio of radiation emitted by the surface to radiation emitted by the black body at the same temperature. So epsilon is between 0 to 1. Epsilon T is equal to ET by EBT. So ET by sigma T power 4. ET is equal to epsilon T sigma T power 4. Diffuse surface properties independent of directions. Gray surface properties are independent of wavelength. So for any body overall, alpha plus rho plus tau is equal to 1. Alpha is absorptivity, rho is reflectivity, tau is transmittivity. So Kirchhoff's law, the total hemispherical emissivity surface at a temperature T is equal to its total hemispherical absorptivity for a radiation coming from a black body at the same temperature. You can write GABS is nothing but alpha G, which is alpha sigma T power 4. E emit is nothing but epsilon sigma T power 4. If G absorption equal to G emission, that is epsilon T is equal to alpha T. View factor, the fraction of radiation leaving from the surface I and falling on the surface J. This is nothing but view factor. So this is not between 0 to 1. The reciprocity rule, AI Fij is equal to AJ Fji. Summation rule, sigma of sigma 11, sigma 12, sigma 13, so on is equal to 1. Radiation of heat transfer. So Q is equal to EB1 minus EB2 by sigma RTH. RTH for a two body system, if you say 1 minus epsilon 1 by A1 epsilon 1 plus 1 by A1 F12 plus 1 minus epsilon 2 by A2 epsilon 2. So this is net radiation between two surfaces. Let us see about chemical kinetics. So chemical kinetics is rate of a reaction R is equal to K into A1 B power 2. So these both combinedly is called as order of a reaction. If I ask individual what is B order, it is 2. Individual A order, it is 1. So combined overall order of a reaction is 3. So K is rate constant, R is rate, B and A is concentrations. So overall radiation is sum of all individual orders. Rate determining step is slowest of the chemical reaction. So zeroth law, epsilon A is equal to A naught minus KT. It will be a straight line in the downward slope. The T half is equal to, put A is equal to A naught by 2. You will get A naught by 2K. For a first order reaction, ln A is equal to ln A naught minus KT. So T half is equal to 0.693 by K. So that it will be a straight line with a downward slope for ln A naught and T. Second order reaction, 1 by A is equal to 1 by A naught plus KT, 1 by A, 1 by A naught plus T. It will be an upward slope with positive direction. The T half is equal to 1 by K A naught. So unit is nothing but concentration power 1 minus N by T. N is the order of the reaction, molecularity. Molecularity is Xa plus Yb is equal to mu C plus Vd. Molecularity is X plus Y. Sum of all this is nothing but molecularity. So sum of stoichiometric coefficient of a reactant taking place in a reaction is this one. Does not change with respect to pressure and temperature. Molecularity. Rate is equal to K into A power M B power N. Order is equal to M plus N. Sum of power raised upon the concentration of reactant in a given rate law expression. Changes with pressure and temperature. Reaction rates for a homogeneous reaction. AA plus BB is equal to CC plus DD. You can write it as 1 by A dA by dt is equal to minus 1 by B dB by dt is equal to 1 by C dC by dt, 1 by D dB by dt. The effect of temperature on the rate of a reaction. So this is nothing but activation barrier. EF is nothing but energy released for the energy released or absorbed for the forward reaction. EB, the difference between them is nothing but activation barrier. Oh, sorry, delta H is nothing but EB minus EF. So K is nothing, this difference, whatever you have, is nothing but your activation barrier. So K is equal to A into exponential minus E by RT. Reaction rates for a heterogeneous equation. Rate of transport of reactants to reaction sites. Chemical rate reaction at the reaction site. Rate of transport of products from the reaction sites. So this is the slowest step of all overall reactions. Will tell you heterogeneous reaction. Actually, this is a 5-step process. If there are two reactants, one reactant coming to the surface, one reactant coming to the surface, then they both reacting, reaching the surface and reacting is the second step, chemical reaction, and then going back, will be the third step. And diffusion is also one which is being part. So diffusion is also one part. Rate of transport of reactants to this. Rate of transport of reactant A, rate of transport of reactant B, chemical reaction at A, rate of transport of products, rate of transport of products. Mass transfer, Na is equal to Kc into delta Cf. Na is molar flux of species A, K is convective mass transfer coefficient, Kc, delta C is concentration difference between boundary surface concentration and the average concentration of the diffusion species. Where Kc is mass transfer coefficient is the rate of mass transfer per unit area per unit driving force. So this gives an indication to how fast will the mass transfer by convection happens. Momentum transfer, mass density is equal to rho is equal to m by v, mass of fluid by volume of fluid. Specific heat, W is equal to W by V, weight of fluid of volume. Specific volume, rho is equal to mu by m, V by m. So anything by mass is specific. Specific gravity, rho of a substance by rho of standard substance. So coefficient of compressibility, beta C is equal to minus 1 by V dou V by dou P. So dP is small change in pressure, dV is small change in volume, V is original change. So coefficient of compressibility is dV by V by dP. Bulk modulus K is equal to 1 by beta C, where beta dV by V. dP is equal to dV by V. Isothermal process K is equal to P. Adiabatic process K is equal to gamma P. Liquids, as your temperature increases, compressibility also increases. But for gases, as temperature increases, compressibility decreases because gases also will try to push each other. Kinematic viscosity. Kinematic viscosity is nothing but mu is equal to mu by rho. Mu is dynamic viscosity, rho is density. So for liquids, temperature increases, mu and V decreases, viscosity decreases because particles move apart from each other. So there is no strong attraction for a strong fluid. As T increases, mu and V decreases. As T increases, mu and V decreases. As T for gases, as T increases, mu and V increases. The wetting liquid, tau should be less than, theta should be less than pi by 2. For a non-wetting liquid, theta will be greater than pi by 2. So this is for non-wetting, this is for rice, this is for dough. So addition between water molecules is stronger. Addition between water and glass is stronger than cohesion between water molecules. Then there will be a small rise. This is called as capillary rise. If there is that's one capillary drop, depression you will be seeing. So rise or depression is nothing but 4 sigma cos theta by rho GD. Laminar flow, individual particles do not cross each other and move along well-defined path. This is called streamline flow or viscous flow. Occurs at low speed and high viscosity. Turbulent flow, fluid particles move in a disturbing way. Newton law of viscosity, tau is equal to mu into dou u by dou y. Mu is equal to dou theta by d theta by dt also you can write. Newtonian fluid, viscosity is independent of velocity gradient. Straight line for tau versus dou u by dou y. Non-Newtonian fluid, viscosity coefficient depend on velocity gradient. Tau is equal to A into dou u by dou y whole power n plus b. Flow behavior index. Consistency index. Ideal solid, real solid. Ideal plastic, pseudoplastic will be like this. And this is a Newtonian fluid. B is a non-Newtonian fluid. And D is dilatant. Pseudoplastic, N is less than 1, B is equal to 0. Milk, blood, clay, liquid cement is pseudoplastic. Dilatant, concentration solution of sugar, aqueous suspension of rice starch. Bingham plastic, ideal plastic fluids, N is equal to 1, beta is equal to tau naught, A is equal to mu. So tau is equal to mu into du by dy plus tau naught. The tau naught is yield shear stress. For ideal solids, rate of deformation is 0. For real solids, deformation slightly at higher shear stresses. Ideal fluids tau is equal to 0. Time dependent fluids. Now let us see about time dependent fluids. Example, thixotropic fluid. Apparent increase in viscosity with times. Non-Newtonian fluids. Rheopectic fluids are viscosity decreases with respect to time. These are called as rheopectic fluids. So flow between two parallel plates. Tau is equal to minus dou p by dou x into b by 2 minus y by 2. This b is nothing but difference between this diameter of the pipe. B is nothing but diameter of the pipe here. So tau max is equal to dou p by dou at b is equal to. So you can say at the center, your when B is equal to 0, your tau max is 0 actually. So at the center, there won't be maximum shear stresses. U is equal to minus 1 by 2 rho minus dou p by dou x into By minus y square. So you can put at U max, you put find the value, you will get 1 by 8 mu minus dou p by dou x into p square. So Q is equal to minus 1 by 12 u, minus 1 by 12 into dou p by dou x into b cube. So Q is equal to mu average into A, mu bar into A, which is 1 by mu into dou p by dou x into p square. Mu by mu max equal to 2 by 3. Delta P is equal to 12 mu bar by B square. HF is equal to 12 mu bar L by rho GB square. U is equal to Vy by B minus 1 by 2 mu into dou P by dou x into By minus y square. So fluid flow in pipes, tau is equal to minus dou P by dou x into gamma by 2 or R by 2. So tau max is equal to minus dou P by dou x into R by 2. So at R is equal to 0 at the center, your tau max is 0. U max 1 by 4 by minus dou. This is in pipes. Don't get confused. This is for parallel plates. This is pipes. There is small difference here. Okay, into R minus R square. You have U max equal to 1 by 4 mu minus dou P by dou x into U. Q is equal to pi by 8 mu minus dou P by dou x into R power 4. Mu by mu max equal to 1 by 2. Delta P is equal to 32 mu bar L by D square. HF is equal to delta P by omega. 32 mu bar L by rho G D square. Continuity equation rho AV is equal to constant. AV is equal to constant. A1 equal to A2. A1 AV1 equal to A2 V2. Differential equation of continuity. Dou P by dou T plus dou by dou X of rho U plus dou by dou Y of rho V plus dou by dou Z of rho W is equal to 0. This is differential equation of continuity. So Darcy equation for head loss is HF is equal to FL V square by 2 GD or 4F dash L V square by 2 GD, where F is friction factor, F dash is coefficient of friction. So you can write F is equal to 64 by RE for laminar flow. HF is equal to FLV square by 2GT. HF is equal to 32 mu VL by rho GT square for laminar flow for both laminar and turbulent. This is for pipes. Bernoulli theorem. So P by rho G plus V square by 2G plus Z is equal to C. P1 by rho G plus V1 square by 2G plus Z1 is equal to P2 by rho G plus V2 square by rho 2G plus Z2 plus HL equal to 0. HL for real fluids. So this is called as pressure head. This is called as velocity head. This is called potential head. So P plus rho G plus Z is nothing but piezometric head. So that is all your heat transfer, kinetics and rate processes. So, okay, that's all.